This video introduces the proof technique, proof by contradiction. So our general strategy is going to be to assume that the entire statement we wish to prove is false. We then show that this assumption leads to a conclusion that is also false. We know that a statement, by definition, is either true or false, but it can't be both or somewhere in between. So if our statement is not false, then it must be true. And that is proof by contradiction. So let's do an example. Let's prove this proposition. If n squared is even, then n is even. And so we are going to do a proof, and we will always assume for contradiction. So that's our way of giving our reader a heads up that we are doing proof by contradiction. Assume for contradiction that, and now we want to do the negation of the original statement. So we want to negate the statement if n squared is even, then n is even. So this is our scratch paper over on the side. It's not part of our proof, but we are wanting to negate that statement, assume that statement is false. And so just in general, recall that the negation of a statement P implies Q is P and not Q. So what does it mean if P implies Q is false? Well, remember in the truth table for P implies Q, there's only one row where that statement is false, and that is false when P is true and Q is false. So that is the logical equivalence of the negation of P implies Q. You could also do a truth table for each of those and observe that that is the case. But anyway, we want to do the negation of if n squared is even, then n is even. And so that means that the negation of this statement is n squared is even and the negation of n is even, so n is odd. So that is the negation of the original statement. So assuming that the original statement we want to prove is false means in this case that we are assuming for contradiction that n squared is even and n is odd. Okay, so we've made this assumption, and now we want to arrive at some kind of contradiction. So there's lots of different contradictions that one could arrive at, anything that is not possible. One thing, for example, is not possible is that an integer cannot be simultaneously even and odd. So let's try to prove, given that n is odd, that n squared must also be odd. And if we're able to show that, then we would have that n squared is even and n squared is odd, and that would be a contradiction. So that is our goal. Show n squared is odd and simultaneously n squared is even, and that would be a contradiction. And we often denote a contradiction by two arrows pointing at each other. So let's try that. So how could we do that? Well, n is odd, so we could say since n is odd, n is equal to 2k plus 1 for some integer k, for some k in the integers. So n squared is equal to 2k plus 1 squared, which is 4k squared plus 4k plus 1 when we multiply out. And can we show that that's an odd integer? Yes, that is equal to 2 times some other integer. 2 times 2k squared plus 2k plus 1 on the outside. So we can write it in that form, where 2k squared plus 2k is an integer. And therefore, n squared is odd. But by hypothesis, n squared is even. And now this is a contradiction and we are done. In case it's not clear, let's talk a little bit about why this strategy works. So some justification for this strategy of proof by contradiction. Suppose we're trying to prove that the statement R is true. We are showing that not R implies a false statement. And so in the example above, our false statement was that n squared is even and n squared is odd. So that was our false statement. But again, this will differ between different proofs. So let's just think about the truth table in general for what we're doing. So we are trying to prove R. And so here's the truth table for R and for not R, which we are assuming. And then we want to look at the column for what does it mean for the negation of R to imply something that is always false. For example, this. Well, remember that when we look at a false statement implying anything, if the original statement is false and that implies something else, we actually don't have to look any further. Every elephant in this room is pink, whatever. Whereas if we have a true statement implying something that does not become true would be false. So this is our little mini truth table for not R implies some statement that is always false. And we see that the column for R, the truth values for R, match up with the truth values for negation of R implies something that is always false. And therefore, these two are logically equivalent statements. So to show that the negation of what we are trying to prove, the negation of the statement that we are trying to prove implies something that is always false, in other words, is a contradiction, is logically equivalent to showing R or proving our original statement R. Okay, so I'd like you to try to do one of these proofs and then we'll talk about it together. So suppose that we want to prove by contradiction that if A, B, and C are in the integers and if A does not divide BC, then A does not divide B. So give this a shot. Use the method of contradiction to prove that, and we will talk about it in just a moment. Okay, so we want to prove this by contradiction. Again, we're going to keep a piece of scratch paper over on the side. So here is our scratch paper. And we first want to think about what we are trying to prove. So if we're doing a proof by contradiction, we want to negate the statement that A does not divide BC implies A does not divide B. And we know that more generally, the negation of P implies Q is P and not Q. So this is logically equivalent to P being true, A does not divide BC, and A does divide B, the negation of A does not divide B. So that's what we're going to assume to begin with. So proof, assume for contradiction, that A does not divide BC and A does divide B. So again, we're trying to eventually come to a contradiction. What is some contradiction we could show? Well, maybe one potential goal is to show that A does divide BC, and we know by hypothesis that A does not divide BC by hypothesis, and this would be a contradiction. So that could be a potential goal. Observe that since A divides B, that means that B is equal to A times, we don't want to use C, we'll say A times K for some integer K, because C has already been used. And so that means that, therefore, BC is equal to, B is A times K times C. And so we see that BC is equal to A times KC, where KC is an integer, and therefore, by definition, A does divide BC. We see that A divides BC and A does not divide BC by hypothesis, and this is a contradiction. So we could write that out in words, or we could have two arrows facing each other, and we would be done. So far, we've used contradiction to prove statements of the form P implies Q, and our general strategy has been to assume the negation of P implies Q, which is P and not Q, and then we were always able to conclude that P was true and not P was true, and this was a contradiction. And so that was basically the format of the two proofs that we've just done. We can also use proof by contradiction to prove other types of statements. So we can use proof by contradiction to prove statements of other forms. Forms aside from P implies Q. So we'll see that in the next couple examples. Let's try to prove this proposition that there exist no integers a and b such that 21a minus 14b is equal to 1. All right, so proof, we want to assume for contradiction the negation of the original statement. So let's just see what that is over on the side. There exist no integers a and b such that 21a minus 14b is equal to 1. If there exist no such integers, then there do exist. If it is not the case that there exist no such integers, the negation of that is that there are integers that make that equation true. So assume for contradiction that a and b are integers and 21a minus 14b is equal to 1. So that is what we're assuming. Now let's think over on the side about what our goal might be. So we're trying to arrive at some kind of contradiction. We are assuming that 21a minus 14b is equal to 1. When I look at that equation, one thing I notice is that on the left-hand side, both of those are multiples of 7. So I could divide the whole equation by 7, and that would give me 3a minus 2b is equal to 1/7. And so over here I have a linear combination of integers, and so this is in the integers, and over here I have something that is not in the integers. So I have an integer being equal to a non-integer, and that is my contradiction. Okay, so let's try to write that out in our proof. Dividing this equation by 7 gives 3a minus 2b is equal to 1/7. Since a and b are in the integers, any linear combination of a and b is also an integer. So 3a minus 2b is in the integers, but 1/7 is not in the integers. 1/7 is not in the integers. We have seen that an integer is not equal to a non-integer. So 3a minus 2b equals 1/7 is impossible, is a contradiction. And so we have finished our proof. This is a contradiction, and we are done. I do want to highlight the usefulness of using scratch paper over on the side. Again, we should be writing things that are not necessarily in the body of our actual proof. And a lot of people, when they're first writing proofs, sort of have issues of, how do I start, and kind of freeze up. And so I would encourage you to get lots of pieces of scratch paper and just feel very free to write lots of stuff down, lots of ideas down, and then hopefully that will help in figuring out what is the logic behind what are you trying to show, so that you can write a proof in logical steps.